Welcome to question 7 of paper 2 of the Higher Maths Leaving Cert 2008 exam. Part A, section 1, Katie must choose 5 subjects from 9 available. The 9 subjects include French and German. How many different combinations of 5 subjects are possible? By the time you reach the exam, you must have already understood the concept of choosing R objects from a set of 9. If you haven't, you must at least remember the notation and formula. Okay, there it is. From n choose r, all in brackets, and that equals the factorial of n over the factorial of r times n minus r factorial. This is called the n choose r formula, and this question fits straight in with no complications, i.e. there are 9 subjects and 5 must be chosen, so the answer is calculated as possible. From n choose 5, and that's n factorial over 5 factorial times 9 minus 5 factorial. And we expand the top and the bottom there, look for cancellations, and see n times 2 times 7, which equals 126. These calculations should be clear. The factorial was already covered in earlier questions in paper 1. So the answer is 126. There are 126 combinations of choosing 5 from 9 subjects. Section 2. Katie must choose 5 subjects from 9 available as usual. How many different combinations are possible if Katie wishes to study German but not French? One of the 5 subjects now must be German, so basically she only has 4 options left to make. She also has 9 minus 1, 8 subjects to choose from, now that German has been taken. But she has decided that amongst those subjects, French is out of bounds for her. So really she now can only choose from 7. So the calculation in this case becomes from 7 choose 4. So as usual we expand. We look for cancellations and find that the answer is 7 times 5, so it's 35. Under these new conditions, there are 35 possible combinations. That's the answer. So we move on to part B, which is about choosing 4 cards from a pack of 52. And then finding the probability in the first section that the 4 cards drawn are the 4 aces. Okay, in this part of the question we're talking about probabilities, not just combinations. This means we must find out the number of ways an event can occur and divide it by the number of possible events. The event we're talking about here is a hand of 4 cards chosen from 52. If we're then told the type of event, we can calculate the number of ways it can happen and multiply it by the probability of having any one set of 4 cards from 52. In fact, this probability is always the same. It only gets multiplied by the number of times the type of event can happen. So let's first calculate the probability of getting one particular hand of 4 from 52. That's 1 all over the total number of possible events, which is from 52 choose 4. So that's from 52 choose 4 in brackets. Again, we expand out the factorials. We look for cancellations and we get 13 times 17 times 25 times 49, which is 270,725. We'll use this number in all 3 sections of this part of the question. But for now, in this part, we must ask how many times 4 aces can occur. Intuition tells us 1 immediately. There are only 4 aces. That card combination is unique. Out of all the possible times, it can only occur once. So the probability of it occurring is once over 270,725, which is, if we calculate using our calculators, 0.3693 times 10 to the power of minus 5. Note that we've used intuition in this case. In the next sections we'll have to calculate this number of ways because the number gets too big for our intuition to help much. Okay, section 2. This time we have to find the probability that 2 of the cards are clubs and the other 2 are diamonds. Okay, so we work out how many times clubs can occur in a hand of 2 first. It's from 13 choose 2. And the same conclusion must occur for 2 diamond cards as well, so it's the same expression. And what do we do then? Well, each combination of diamonds, say, will make the 4 card hand different, even if the 2 club cards don't change. So we multiply, or, which is the same thing, we calculate the square of from 13 choose 2. As I've done 2 n choose r calculations already in this question, I won't evaluate this expression and just say it comes out to be 13 squared times 6 squared. We now need to divide this by 270,725, though it's better to use the factored form, which we found out. So we get 13 squared times 6 squared all over 13 times 17 times 25 times 49. And we look for calculations again and simplify, and we get 0.0225, which is our answer. So we move on to section 3. This time we have to find the probability that there are 3 clubs and 2 aces among the 4 cards. It should be clear that one of the cards needs to be the ace of clubs. There is only one of these, so in fact we can concentrate on the remaining 3 cards now, as it will not affect the calculation, as long as we remove it, that's the ace of clubs, from the card deck. However, for the second card in our hand, we need another ace of the 3 that are left. So that means that there are from 3 choose 1 possibilities. So what are the remaining 2 cards? The question tells us they must be clubs, and as the ace is gone, this must be from 12 choose 2. Multiplying these together, we get 3 times 12 times 11 all over 2, which is 18 times 11, and we need to divide this now because we need to get the probability. And we choose the factored form, which we discovered, which is 13 times 17 times 25 times 49. And the answer should come out to 198 over 270,725, which is 0.731 multiplied by 10 to the minus 3. And that, in fact, is the answer. I'll just go back there so you can take a note. That's the answer. We move on to part C now, which has not got to do with probability. We're given 3 x's, x1, x2, x3, and the average x bar. And we're also given an expression for the distance of each of the x's from the average of x. And we have to show that the sum over 3 of dr is equal to 0. We should start by giving more detail about what x bar actually is by using its general form, which is xr over n summed over n is the average of x, which is x bar. So in this case we get, there are only 3 x's, n is 3, so we get x1 plus x2 plus x3 all over n. Now we can expand the sum as given, for the sum for dr, and say basically we just substitute our xr minus x bar for d, and we can regroup all the x bars and then substitute our expression for x bar and get as shown. With this expression it's clear how it all cancels to 0. We see the x1 plus x2 plus x3, the 3's will cancel, and we see it being subtracted by x1 plus x2 plus x3, so that has to equal 0. So we move on to the last part now, the arithmetic mean of the 3 numbers. Again, it's the same situation as x bar. This time we're talking about standard deviations. We're given k squared is equal to sum of dr minus b squared over 3, and we have to show that sigma squared is equal to k squared minus b squared. You should know that the standard deviation is only slightly more complicated than calculating the average, which means that it's quite straightforward. The formula is there as given, which is the sum over xr minus x bar all squared over n, and the square root is taken of that. Our job now is to show how we can take away b squared from the given formula for k2 given in the question and get the standard deviation squared. Like in section 1, we can just expand k squared first and show how, by subtracting b squared, we can get sigma squared. We should also keep an eye on the single dr terms, because in section 1 we proved that the sum over 3 of that was 0. Okay, so there we get the expression. We expand it out, and what we do then is we divide it into 3 sums. What we've done here is distribute the summing operations to parts of the sum, okay, which is valid. And we see, in this way we can see that the middle terms, where we have the sum over 3 of a single dr, okay, will go to 0 as seen in section 1. So what are we left with? Well, we're left with the first and the third terms. Of course, as a real number, b will not change over the sum. It will merely get added to itself 3 times, and since it's being divided by 3, this second term is just b squared. But we're being asked to subtract b squared from this to get sigma squared, so we can now forget about the b squared term. So we're only left with 1 now, which is the sum of dr squared over 3. So we can expand that, substitute our value for dr in there, And we actually see that this is the standard deviation formula we mentioned in the beginning, with n equals to 3 and without the square root. So now it's clear. The answer is sigma squared, and we've proved the expression.